Today's lecture is on strong induction. It is a variation of the weak induction that we have been talking about in the last lecture. Just to recall, the weak induction is when we can show proposition is true for the base case directly, and then prove that proposition is true for n implies the proposition is true for n plus 1. So to apply induction to any problem, we need to be able to use the discrete nature of the natural numbers or be able to enumerate the problem so it can be described using n. So let's get started. So first we're going to talk about something called the well-ordering property, which says every non-empty set of non-negative integers has a least element. So the well-ordering principle says that every set of non-negative integers has a least element. Do we believe that? Well, intuitively, it sounds reasonable, but notice how tight it is. It requires a non-empty set. It is false for empty set, which has no smallest element because it has no elements at all. And it requires a set of non-negative integers, and it's false for the set of negative integers, and also false for some sets of non-negative rationals. If you consider the rationals such as 1, 1/2, 1/3, this set has no least element. So the well-ordering principle captures something special about the non-negative integers. It is a fundamental axiom of the set of integers, which we want to believe to be true. So the validity of both the principle of mathematical induction and strong induction, which we will learn, follows from it. We will show how the well-ordering property can be used directly in proofs. Furthermore, it can be shown that the well-ordering property, the principle of mathematical induction, and strong induction are all equivalent. So let's start with a problem. We want to prove that for any positive integers m and n, the fraction m over n can be written in the lowest term using well-ordering principle. So the fact that every fraction of the form m over n can be written in lowest form is a result that we continue to use in our proofs of rational numbers. Intuitively, it sounds reasonable that because if it is not, we can find a common factor and divide both m and n by that common factor. And then we continue until there are no more common factors. But intuition is not a proof technique. It needs to be done by a solid proof. So the question to ask is, how do we know that this process actually ends at some point? So in other words, for this process to end, we have to reach a minimal ratio m over n that has no common factors. So let's think about a solution for doing that. How would you prove this using the fact that the axiom, the well-ordering principle that says every non-empty subset of non-negative integers has a least element? So here are the steps to think about. So here's the proof. So let's suppose that there exists some m and n such that m over n cannot be written in lowest terms. So let's define a set C, which is a set of all these m's in Z plus, the positive integers, where the m over n cannot be written in the lowest form. So in other words, these are the set of all numerators of the numbers of the form m over n, where they cannot be written in lowest form for whatever the reason. So because we think that suppose if you assume by contradiction, suppose there's something here that cannot be written in lowest form, then we know C is non-empty by our assumption. So by well-ordering principle, there exists some m naught in this set C, which is the smallest, because we know the well-ordering principle says every non-empty subset of non-negative integers has a least element. So there's some least element called m naught in C, or in this set C, such that m naught over n naught cannot be written in the lowest form. So if this cannot be written in the lowest form, that means they still have a common factor. Let's call that P. So now we look at the ratio m naught over P divided by n naught over phi, Therefore, this also cannot be written in lowest term. Hence, we prove that m naught over p is in C. All right, and therefore, but m naught is the lowest term in C. The fact that m naught over p is in C and m naught is the lowest term contradicted the fact that m naught over p is less than m naught. So going back to this proof, so again, what we're trying to establish is that we assume a minimum number, and then we show that if there's a common factor, we can find another number that's less than the minimum number we assume. Therefore, we reach a contradiction. So proofs using well-ordering principle has few properties. We want to prove that Pn is true for all n in some n using the well-ordering principle. So basic approach is that to define a set C of counterexamples where P is to P being true. In other words, we want to define the set C as the set of all n in n such that Pn is false. So assume for proof of contradiction that C is non-empty, because if it's empty, then we have proved the Pn is true for all n. But if there's some n where the Pn is false, then there has to be some element in C, therefore C cannot be empty. So by the well-ordering principle, there will be a smallest element in C. So we could find something in C, and then what we tried to do in the previous example is to try to reach a contradiction somehow, often by showing how to use n to find another member of C that is smaller than n. So in other words, but this is an open-ended part of the proof task, and it varies from proof to proof. So you have to think about each proof to see how to construct this contradiction. So then we conclude that it couldn't happen, therefore C must be empty. So that means there's no counterexample exists where Pn is false. What that means is Pn is true for all n. So once again, we can use the well-ordering principle to prove that a proposition is true for all n in n. In order to do that, we define a set of counterexamples and show that by contradiction, this set has to be empty. And therefore, no such n exists where the Pn is false. Therefore, Pn must be true for all n. Okay, so let's take a look at this example where we want to prove that 2 to the n is greater than n for all n greater than or equal to 1. This seems to be true. You can see that 2 to the n actually grows much faster than n. We can easily prove this by ordinary induction, but what we are going to do is to construct a proof by well-ordering principle. So here's the proof, how we're going to build the proof. So what we want to show is that 2 to the n is strictly greater than n for all n greater than or equal to 1. So let Pn be the proposition that 2 to the n is greater than n for all n greater than or equal to 1. So let's construct a set C where set C is the set of all n where the Pn is false. That means if we can find a counterexample for this to be false, that means this is not true for all n. So we couldn't prove it. So we want to show that C is in fact empty, but to show that we assume C is not empty. So proof by contradiction. Suppose there is some n such that Pn is false, therefore C is not empty. So C is not empty, that means by well-ordering principle, there's a smallest element n naught in C. So because it's in C, it contradicts this assertion, which is 2 to the n is greater than n. So the assertion, it satisfies the Pn is false, which is 2 to the n naught is less than or equal to n naught. Now we know that 2 to the n naught minus 1, which is in fact 2 to the n naught divided by 2, is strictly less than 2 to the n naught. For now, I'm just going to consider the case that 2 to the n naught is strictly less than n naught. So we know that 2 to the n naught is strictly less than n naught. Now since n naught is, because if 2 to the n naught is strictly less than n naught, which means that 2 to the n naught minus 1 must be less than or equal to n naught minus 1. So this proves the fact that the The proposition is also, there's another element, n naught minus 1, which belongs to C if n naught is there. Now, the other case where if the 2 to the n naught is equal to n naught, then we clearly know that 2 to the n naught minus 1, which is really 2 to the n naught divided by 2, that's n naught over 2, which has to be, intuition tells us that that's got to be less than n naught minus 1, n naught divided by 2. So therefore, we can show that there's another element in C which is equal to n naught minus 1, which is less than our minimal assumption n naught. So that's a contradiction. And therefore, we will conclude that this set C must be empty. That means there is no n such that Pn is false, and hence 2 to the n is greater than n is true for all n. So let's compare the ordinary versus weak induction. Ordinary or weak induction is the easiest to explain. In other words, ordinary or weak induction says that rule 1 says P naught is true, some base case. And then we assume Pn and then try to prove Pn plus 1. So as we learn that first, for the most part, we can easily prove lots of facts about number theory using weak induction, such as the sum of the 1 plus 2 plus up to n is n over 2, n plus 1. So the strong induction, in fact, is pretty similar, but it lets you do this. You have to still establish the base case directly, and then you're allowed to assume all of the propositions from P1 to Pn to be true, and then you want to show that that implies Pn plus 1. It's called a strong induction because it assumes everything between P1 and Pn, right? But this, as you can see, these two are equivalent things, except the fact that by using this, sometimes it's easier to prove things. All right, so we'll take a look at some of those things in the coming slides. So the strong induction can be very useful if we do need more than one assumption. Because in weak induction, we just have Pn, we have to show Pn plus 1. But strong induction, we are allowed to assume everything up to Pn. So it can be more than one assumption. So we might assume Pn and Pn minus 1 is true, and then we show that Pn plus 1 is also true. So the well-ordering principle, weak induction and strong induction, are mathematically equivalent and are very good, powerful techniques. So let's see some very important applications of strong induction next. So a theorem. It says that prove that any integer n greater than 1 is a product of primes. That is, if you're given an n, it can be expressed as a product of prime numbers, where each one is a prime. So we'll prove this statement by strong induction. So here's the proof. So let Pn be the proposition that any positive integer strictly greater than 1 can be expressed as a product of primes, including 2. We are starting from 2 and going up. So base case is that we know that P2 is true, since 2 is a prime itself. So inductive step, we assume that suppose that for any n greater than 2, Pk is a product of prime for all k between n and 2. In other words, we assume that the proposition is true for any k between 2 and n. In plain English, this means that we assume any integer less than or equal to n and greater than 2 can be expressed as a product of primes. Now we need to show that Pn plus 1 or n plus 1 is also a product of primes. So if n plus 1 is a prime, that's one case, then Pn plus 1 is true and we are done. If n plus 1 is not a prime, then we can express the n plus 1 as a product of primes, which means that n plus 1 is going to be m times p, where m and p are integers less than or equal to n. But by induction hypothesis, we know that m and p can be expressed as a product of primes because m and p are both less than n. So they fall into this group of things we assume to be true. So therefore, we prove that n plus 1 also can be expressed as a product of primes, hence Pn is true for any n. So it's a very powerful theorem that we prove that any integer n can be expressed as a product of prime numbers. So here's another example. We want to show a proof here that if you have this sequence of things, a1 is 1, a2 is 3, and the ak is expressed in terms of ak minus 2 and ak minus 1 for all the integers greater than or equal to 3. We want to show that this sequence of things is always odd. Each term is always odd. So how do we show that using strong induction? So we know the base cases P1 and P3 are true since 1 and 3 are odd numbers. So if you look at these, the first base case 1 and 3, they're odd numbers, so that's true. Suppose assume the pk is true for every k from 1 to n. So that's the inductive hypothesis. We want to show that Pn plus 1 is also true. So the Pn plus 1 says the sequence An plus 1 is odd. Obviously, I'm not writing this as a subscript. So this is really a subscript n plus 1. So by definition, a to the subscript n plus 1 is a subscript n minus 1 plus 2 times an, which is as given here. And so because we know both an minus 1 and an are odd numbers, we can express them using the form 2k plus 1 and 2l plus 1. Since by induction hypothesis we know these are odd numbers. We do some simplification to this, this term on the right-hand side, and we obtain, you can see the mathematics here, we obtain a expression of the form 2p plus 1, where p is equal to this quantity here. So what that means is a of subscript n plus 1 is also odd. So notice in this case we had to use strong induction because we had to assume both, not just an to be true to show an plus 1, we had to assume both an minus 1 and an are true to show that an plus 1 is true. So we'll look at the next, an interesting example of using postage. So we want to show that every amount of postage can be, that is at least 12 cents, can be made from 4 cent and 5 cent. So in this case, we are using strong induction to prove something really interesting, that if you only have 4 cent and 5 cent stamps, we're going to claim that any amount of postage that is at least 12 or more, so it could be 12, 13, 14, 15, and so on, can be made from 4 cent stamps. So let's take a look at how to prove this. So for example, we want to know whether this is actually true before we start proving it. We know that 12 cent uses 3 4 cent stamps. 13 cents can be made using 2 4 cent stamps, that's 8, plus 5 cent stamp, which is 13. 14 uses 1 4 cent stamp plus 2 5 cent stamps, and so on. So if you experiment with small values, you quickly realize that the formula for making k cent stamps depends on the one for making k minus 4 cents of postage. So that is, if you take the stamps for k minus 4 cents, add another 4 cent stamp, we can make this into an inductive proof as follows. So let's do by induction the amount of postage. The base case is if the postage is 12 cents, we can make it with 3 4 cent stamps. We know that. That's a base case. If the postage is 13 cents, we can make it with 2 4 cent stamps plus 5 cent stamp. If it's 14, we can use 1 4 cent stamp plus 2 5 cent stamps. If it's 15, we use 3 5 cent stamps. So we know that the proposition is true for 12, 13, 14, 15. So suppose that we have to show how to construct postage for every value from 12 up through k. So in other words, we need to show that how to construct k plus 1 cents of postage stamps if we know that P12 through Pk is in fact true. That means any number from 12 to k can be done using 4 cents and 5 cent stamps. So we need to show how to construct this k plus 1 cents of postage stamps. Since we have already proved the base cases up through 15 cents, we can assume that k plus 1 is greater than or equal to 16. And since k plus 1 is greater than or equal to 16, k plus 1 is minus 4 is greater than or equal to 12. So by inductive hypothesis, we can construct the postage for any k plus 1 minus 4 cent stamps using M 4-cent stamps and N 5-cent stamps. So we know that because by induction hypothesis, this is true for anything. So let's assume that given any k, we would be able to do that. So in other words, k plus 1 minus 4 is going to be M 4-cent stamps and N 5-cent stamps. So, but then k plus 1 is 4 times M plus 1 plus 5N based on this formula here. This means that so we can construct k plus 1 cents of postage using M plus 1 4-cent stamps and N 5-cent stamps, which is what we want to show indeed. And we can take a look at this as a demo program. In fact, you can write the recursive function which allows you to prove that this is in fact can be done. We will look at the Java program in another slide. So final thoughts on strong induction, and well-ordering principle. Strong induction seems to be much stronger assumption than regular induction or weak induction or ordinary induction, but this is not really the case. It's not too difficult to imagine that an automated program can reformat any proof using strong induction into a proof using ordinary induction, because ordinary induction can also prove that the strong induction is the equivalent. To use strong induction or not can be followed by the fact that to prove Pn plus 1, if you just need Pn or need assumptions like Pn minus 1. So if you need both Pn and Pn minus 1 to show Pn plus 1, then you must use strong induction. So if you recall, the well-ordering principle states that any subset of integers has the smallest element. So most proof that involves well-ordering principle can be reformatted to be an inductive proof. So the three proof techniques, ordinary induction, strong induction, and well-ordering principle, are equivalent proof techniques, and they can be used to present the same mathematical reasoning. So they are very good tools in your arsenal of proof techniques, and induction is very powerful as long as you can enumerate the problem into some way of describing using N.